Welcome to the second part of gas cycle in thermodynamics. In the first lecture, we saw what is air standard cycle, then we saw Otto cycle. Now, we will see diesel cycle. So, friends, you would have enjoyed traveling by a diesel car, bus, train. So, diesel trains are also there. So, diesel cycle is one of the most popular cycle. So, when we go back, it finally boils down to PV diagram and TS diagram. So, diesel cycle consists of two isentropic reversible adiabatic process, one isobaric reversible constant pressure process and one isochronic reversible constant volume process. So, there are four processes, because if you have a box, there are four processes 1, 2, 3 and 4. So, it is said that two of them are isoentropic in nature. What is isentropic? And it is also reversible adiabatic. It is very important. Adiabatic is also very important. We have seen what is adiabatic, reversible cycle also we have seen. Then one is isobaric. So, it is again reversible constant pressure, because bar pressure, right. Then one is isochronic. So, which is constant volume, and all the processes are reversible. The cycle was proposed first by Rudolf Diesel in 1890. So, he proposed a cycle, then subsequently lot of technologies were developed and then these two got merged. The diesel cycle is the ideal cycle for compression ignition engine. We call it as CI. Petrol is called as SI, spark ignition. This is compression ignition. So, it clearly says compression, compress and then it ignites. Unlike spark ignition engine, combustion in diesel is initiated by the high temperature of compressed air, into which the fuel is injected. This results in high thermal efficiency. The cycle led to the development of technology. You can see there will be a big difference in the engine design itself. So, here in diesel, you will have an inlet valve, outlet valve, which is controlled separately. But whereas when you go to petrol, it is done in the inlet fold and then outlet fold are there in one side. So, there is a high thermal efficiency. So, why is that thermal efficiency high? Here it is compressed and it ignites. There it is trying to compress and then there is a spark which is there which tries to ignite. So, when the exhaust happens, maybe there is a possibility of rich fuel getting removed out without burning. It is possible in petrol, but diesel it is reduced to a large extent, especially at part load condition, making the diesel engine widely used in heavy duty vehicles, marine applications and power generation. You can also use diesel cycle in power generation, which is nothing but DGs, diesel generator. As I told you, PV diagram, we are going to look into PV diagram and TS diagram, pressure volume diagram, temperature entropy diagram. So, the cycle starts from 1 here, V1, the volume is 1 and then the volume is compressed. If you go back and if you want to visualize, you have a cylinder and then you have a piston, right. So, the volume is reduced from V1 to V2. Okay. Once it is reaching the highest value, So then there is a Q which is introduced, and we make sure the pressure is constant. So now the piston is at its maximum position. The piston is at maximum position. Then after it has reached its maximum position, and when the Q is injected, the Q which is there, the heat whichever is there, so it is trying to ignite, and afterwards it will try to move down. When it is trying to move down, then the pressure will be reduced, the volume is expanded, which is from 3 to 4. The process 1 to 2 and 3 to 4 follows reversible adiabatic process. 2 to 3, it is a constant pressure process. Once it has reached the lowest value or the stroke end of the piston, then from 4 it tries to go to 1. So at this point it is constant volume process. So 2, 3 is constant pressure process which is reversible. 4, 1 is again a constant volume process which is reversible. This is what we have said here. It has 2 isoentropic reversible adiabatic which happens between 1 to 2 and 3 to 4, and then isobaric which is constant pressure 2 to 3, and we said constant chronic is between 4 to 1. So between 4 to 1 the heat is extracted. So when I draw the corresponding TS diagram for the same, you can see temperature versus entropy. The process starts from 1. So from 1. When there is a compression which is happening, the temperature increases to 2. Why? Because the volume is compressed. The volume is compressed. When the volume is compressed, there is naturally a temperature increase. Then afterwards what happens is from 2 to 3, where you are trying to put an input Q, there is a constant pressure process, and during this time the entropy increases from 2 to 3. The entropy increases. Then from 3 to 4, when there is an expansion happening, the entropy remains constant. And from 4 to 1, once there is a constant volume, the entropy reduces from 4 to 1. When this happens, you see constant pressure and constant volume. So isentropic compression happens at 1 to 2. In this step, the piston moves upward, as I told you before, compressing the air fuel mixture inside the cylinder. The compression happens rapidly without heat exchange. That is why it is called as adiabatic. Constant temperature. So the compression happens rapidly and without heat exchange. Without heat exchange to the atmosphere, that is why it is called as adiabatic. So the temperature and the pressure of the gas increases significantly. Temperature increases, the pressure increases. This process stores energy in the form of increased internal energy, which we have already seen is U. Now let us go to the next step, 2, 3. Please note down PV diagram 2, 3 and TS diagram 2, 3. It is called as constant volume heat addition process. Q is getting added. Okay. At the end of compression, an ignition happens in the air fuel mixture. The combustion occurs quickly and heat is added at constant volume. So if you see here, volume is constant because the piston is momentarily at the top dead center. This sudden addition of energy causes the pressure and temperature of the gas to rise. The next one is isentropic process. where it is otherwise called as a power stroke. It happens between 3 to 4. The pressure gas now pushes the piston down because there is a closed area. The piston is at its topmost position and here the ignition has happened. So, now there is lot of temperature, the pressures are very high. So, what is left is this fellow has to come down, the piston has to come down. So, the high pressure gas now pushes the piston down, doing useful work on the crankshaft. So, now this other end is attached to a crankshaft and that in turn is attached to an engine. So, crankshaft. This expansion occurs without any heat exchange. That is why it is called as adiabatic. Without any heat exchange. So, it is called adiabatic. As the gas expands, its temperature and pressure falls down. This is called as a power stroke because it is moving down. The other end of the piston is attached to the crankshaft. Now, the crankshaft rotates. So, once it rotates, it is further attached to the engine. The last step is going to be constant volume heat rejection 4-1. Where is it? 4-1. 4-1. PV diagram 4-1, TS diagram 4-1. It is constant volume heat rejection. Once the piston reaches the bottom dead center, this is TDC and this is BDC. Bottom dead center, the exhaust valve opens in the top and the gas is cooled at constant volume, rejecting heat to the surrounding. That is what is happening in the exhaust. When you try to drive a bike or when you try to drive a car, diesel, or when you try to drive an engine, you will always have an exhaust which comes out, right. So, that is nothing but once the piston reaches the bottom dead center, the exhaust valve is open and the gas is cooled at constant volume, rejecting heat to the surrounding. This reduces the pressure and temperature of the gas, completing the cycle and preparing the system for the next cycle. So, friends, we are just playing around P increase, T increase, P decrease, T decrease, having a constant volume, and this is done by a piston cylinder assembly, and this fellow rotates. Okay. So, here you attach it with the gear. So, this rotates, this moves up and down, this is stroke. This is TDC and this is BDC. This is what is that, friends? Diesel cycle. So, if you understand this diagram, and the only thing you have to understand is pressure increases, pressure decreases, temperature increases, temperature decreases. The volume can be constant or the volume also can be increase or decrease. So, these are the three parameters you play, and this is done by a cycle. When you call a cycle, it starts and ends at the same point. So, that is why it is called as a cycle. Now, continuing from there, so the heat supplied, Q supply, is between 2 to 3. So, if you go, you can see a diagram like this. So, maybe 1, 2, 3, 4. So, you can see 2 to 3 is the heat supply, that is written as MCP T3 minus T2. This TS diagram, right. Then it is heat rejection will be between 4 and 1. So, here this is in and this is out. So, it will be MCV T4 minus T1. Now, if you want to calculate the efficiency, it is nothing but 1 minus Q reject by Q supplied. That is nothing but 1 minus, you write the full equation, then you write this full equation, this and this, and then you try to bring it to that level. When you substitute it, it gets converted into 1 minus T4 by T1 divided by 1 by gamma, adiabatic ratio, T3 minus T2. So, now if you write it in the efficiency equation, it is going to be 1 minus T1. So, I am just dividing this T1 by 4. So, T4 by T1 minus 1 divided by T3 by T2 minus 1 gamma. To recall, the process 1 to 2 is isentropic or reversible adiabatic compression. When we talk about 2 to 3, it is isobaric. 2 to 3 is isobaric. Isobaric means constant pressure, right? And then 3 to 4 is isentropic, which is a constant volume. So, 1 to 2 is a reversible adiabatic compression and 3 to 4 is a reversible adiabatic expansion. So, to define the volume ratio, we try to take RC is nothing but V1 by V2. This is for compression, and for expansion it will be V4 by V3. So, there is something called as cutoff ratio, which is rho is equal to V3 by V2, which is rewritten as RC is equal to RE into cutoff ratio rho. So, this is very important, friends. You can expect a 2-mark problem in this equation. So, a similar equation will be discussed in multiple cycles. So, you have to just understand that. So, now when we try to write it for 1 to 2 process, as usual it is straightforward T2 by T1, which is nothing but, so how does it come? It is V1 by V2, the whole power gamma minus 1. So, it can be rewritten like this form, and this is the end form. When we try to talk about isobaric, it comes to rho, that is nothing but the cutoff ratio. Right. So, the next one is when we talk about isentropic reversible adiabatic expansion, T4 by T1 is equal to rho times cutoff ratio times gamma. So, on substituting in equation 3, we try to get this cell is 1 minus this, and this can be rewritten as this form. So, this is the final equation to find out the efficiency of a diesel cycle. So, the mean effective pressure PM, which we saw last time also, the or MEP is expressed as PM is this form. So, it is basically trying to play with all these parameters. You try to juggle it and then get this form. Now, let us try to compare Otto cycle and diesel cycle. Otto engine is homogeneous mixture of fuel and air formed in the carburetor is supplied to the engine cylinder. It is a homogeneous mixture of air fuel. So, that is why we always talk about air fuel ratio. Air fuel formed in the carburetor. So, what is carburetor? Is a part where there is a mixing of fuel and air. Liquid comes from one side, petrol comes from one side, air is drawn inside through in front of carburetor. At the carburetor there is a mixing happening. So, the fuel and air formed in the carburetor is supplied to the engine cylinder. Next, once it is supplied, then there is a ignition which is initiated by a spark plug. So, when you have compressed completely, the cylinder piston goes very close. When you have compressed, then there is a spark plug which tries to spark. Moment it tries to spark, there is a very small place where air fuel mixture is there and it is rich. So, moment it is there, the spark ignites, then there is a reaction, then this tries to push the piston down. So, that is what it says. Ignition is initiated by means of a spark plug. So, in petrol engine you will always have a spark plug. So, the power output is controlled by varying the mass of the fuel air mixture. So, you can make it rich, you can make it lean. So, the power output, with what power it comes out, is called as a power output, is controlled by varying the mass of air fuel mixture by means of throttle valve in the carburetor. So, basically when you are trying to drive a car or a scooter, you try to accelerate. When you accelerate, what you do is there is a cable which connects the accelerator to the carburetor. Moment you start accelerating, the cable starts pulling. So, in the carburetor there will be a valve which is opening to maximum, and when you try to release it, it shuts down. So, once it shuts down, the air fuel mixture is brought to almost lean state. Okay. This is what happens in the Otto engine. When we talk about diesel engine, there is no carburetor. So, here the air alone is supplied to the engine cylinder. The fuel is injected directly into the engine cylinder at the end of the compression stroke by means of a fuel injector. The fuel air mixture is heterogeneous. Same, whatever we talked about here in diesel engine also, the compression comes to the dead. If you have a cylinder, this is your top dead center. Till here the piston will come, and here you will have your spark plug. So, now instead of spark plug is removed, the carburetor is removed. So, there is a air which is directly getting supplied into the engine. The fuel is injected directly into the engine cylinder at the end of the compression stroke by means of a fuel injector. So, if you see a fuel injector, it will be something like this. It will have a cone and it will have holes. Through these holes, you spray the diesel inside a cylinder. So, the cylinder at the end of the compression stroke by means of a fuel injector. The air fuel mixture is heterogeneous in state. So, here we do not use a spark plug. The compression ratio is high and the temperature of the air ignites the fuel. That is the difference. So, here you have a spark plug. In diesel, we do not have a spark plug. So, no throttle valve is used. So, here you used a throttle valve in scooter or in car, I said. Here, no throttle valve is used. The power output is controlled by means of mass of the fuel injection by the fuel injector. So, the amount of fuel getting injected. So, here what happens? The throttle, whatever I said in accelerator, is directly connected to the fuel injector. So, it is a very interesting thing. If you see diesel, when you fill it up, it is at a normal atmospheric pressure. It is a tank filled with diesel. Now, you have an engine on the other end. This engine has to be injected the fuel, and what gets injected in the fuel, it is not like a pipe pouring there. So, you have to increase the pressure, not the temperature. So, what we will do, from the tank we move it towards a pump. So, in the pump you try to increase the pressure. So, when you try to increase the pressure, you should increase it to such a fashion what gets coming out of the injector should all be in droplets. So, it is almost you have a pipe, when you press the pipe end in the while watering the garden. So, you will see small droplets of water coming out, or you put a sprinkler, you see the water gets atomized. So, diesel also has to be atomized, and the atomized diesel through the injector is pushed into the cylinder. So, that is what is happening here. So, now what amount of fuel to be injected is the mass of the fuel injector. Is that clear, friends? Okay. So, now let us try to take a combination of Otto cycle and diesel cycle, which is called as a dual combustion cycle. In early compression injection engines, the fuel was injected when the piston reached the top dead center, and thus combustion lasted well into the expansion stroke. The air standard diesel cycle thus does not simulate exactly the pressure volume variation in an actual modern compression injection engine. So, in modern engine, the fuel is injected before the top dead center about 15 degrees. So, where is this top dead coming up? Because I cannot control the displacement inside the engine, but where in which I try to take the output of this and connect it to a crank. So, now I try to talk about the angle what it can do with respect to 0, 15 degrees. Right. So, the dual combustion cycle is the closer approximation to the modern compression injection engine, in which some part of the heat is added to the air at constant volume and remainder at constant pressure. Look at it. How does it happen? So, you will have 1 to 2 is compression, then 2 to 3 you see there is a constant volume, but there is a pressure increase. From 3 to 4 there is a expansion which is happening, 3 to 4, and then from 4 to 5 there is a complete expansion. So, when we say 3 to 4 there is a constant pressure. This is what is dealt in the last para. The dual combustion cycle is the closer approximation to the modern compression ignition engines, in which some part of the heat is added to the air at constant volume. So, this is the constant volume. Between 2 to 3 you inject heat, then again 3 to 4 when the pressure is constant you inject. So, this is called as a dual combustion cycle. So, 4 to 5 is reverse adiabatic, 1 to 2 is also reverse adiabatic. So, this PV diagram clearly states how does a dual combustion cycle work. Now, let us go to TS diagram, because for us S is very important, entropy, right. So, TS diagram. So, in this what happens, from 1 to 2, when we move from 1 to 2, there is a reduction in the volume. So, compression happens. So, during compression the temperature is constant. During 1 to 2 the temperature is constant. So, S is also constant. For a fixed entropy, the TS diagram clearly shows that how what happens to the entropy in terms with respect to temperature. So, 1 to 2 there is an increase in temperature with a constant entropy. There is no change in the system. From 2 to 3 where I raised the pressure keeping the volume as a constant. So, you can see volume constant. From 2 to 3 what happens? The temperature increases, pressure increases, temperature increases, entropy increases. Then from 3 to 4 where I maintained a constant pressure, you can see again there is a increase in entropy and the temperature. From 4 to 1 it is nothing but an expansion cycle. 4 to 1 you can see the entropy is constant. So, 4 to 5 there is an expansion which is happening. So, 4 to 5 when you look at a TS diagram there is a decrease in temperature and entropy is constant. So, then 5 to 1 the volume is constant. So, 5 to 1 the entropy reduces. The entropy reduces from S2 to S1, the temperature also reduces. So, this PV diagram and TS diagram clearly shows the dual combustion cycle advantage. So, isentropic compression is 1 to 2, we have already seen. 1 to 2 is isentropic compression. So, in the first step the piston compresses air inside a cylinder without any heat exchange. Since the process is adiabatic and reversible, the pressure and temperature of the air increases significantly. This prepares the gas for effective combustion. When we go to 2 to 3, it is a constant volume heat addition. At the end of the compression stroke, a portion of the fuel is injected and combustion happens very rapidly, causing a sudden rise in pressure and temperature. So, 1 to 2 also pressure and temperature increases. So, after heat is given, pressure and temperature increases at a constant volume. This step resembles the heat addition in the Otto cycle. Then 3 to 4, it is a constant pressure heat addition which we saw in the PV diagram top. So, following the initial constant volume combustion, the remaining fuel is injected and burns more slowly while the piston begins to move down. So, at the top dead center you have hit Now slowly it will be moving down. So following the initial constant volume combustion, the remaining fuel is injected and burns more slowly. That is injected and it burns more slowly, while the piston begins to move down. This allows the heat to be added at constant pressure, further increasing the temperature and the volume of the gas. So volume increases, temperature increases. This phase is similar to diesel cycle of heat addition process, which is there. So that is why it is called as dual cycle. Now the 4 to 5 is a isentropic expansion. Very high temperature, very high pressure, the gas expands adiabatically and does useful work by pushing the piston down. As the gas expands, its pressure and temperature drops, because moment the volume increases, the pressure reduces, the temperature also reduces. There is no heat exchange with the surrounding. So this means the power producing stroke of the cycle is the 4 to 5 stage. Friends, now you will be able to enjoy and understand what is a Otto cycle, what is a diesel cycle, what is a dual combustion cycle. So all these things are very important, because when you are trying to go in a car, or when you are trying to go in a bus, or when you are trying to go in a diesel engine, you should now understand what happens inside the machine. There should be some piston moving, cylinder moving, some part moving, some mechanical part doing something. But what is the science behind it? That comes from the thermodynamics. So first they did thermodynamics, they understood the science. From there they moved to a technology. Today they are working very hard to optimize the technology to get maximum efficiency. And the efficiency, whatever we are calculating here, is ideal efficiency. So that means to say, we will not consider there is a drop in temperature, or what we measure T2 and T1, it can be static or it can be dynamic, right? All these things happen. The volume V1, V2, whatever we measure, we assume that there is no stray volume left, there is no stray air mixture left, there is a residual cleaning. And once we try to convert the science into technology, you will always try to have a different valve opening time and closing time, the height of the valve changes, the response time changes. So all these things are dynamic. So we don't consider any of them. We don't consider the wear and tear. We don't consider the working fluid. So throughout you see, where have we considered the working fluid? Say for example, you have a petrol which is used, or a diesel which is used in a high speed car, in a high speed plane, in a normal plane, in a normal car, whatever it is. So we don't compare the quality of the working fluid. We don't compare the specific heat it can produce, nothing. We do it only by science, and we try to assume all other things zero, we try to derive it. So the efficiency, whatever we derive from here, it is all theoretical efficiency. These theoretical efficiency, there will be almost a drop of 50% to actual efficiency. So if you see the diesel cycle, Otto cycle, what we study through here, you will try to get efficiency 40%, 50%. In some case, academically or theoretically, you can get even 70%. In reality, it will be close to 25%. So we saw 4 to 5, this is the power stroke. Then 5 to 1 is the heat rejection cycle. Whatever we have discussed till now, we have presented here. Finally, at the end of the expansion stroke, the gas is cooled at constant volume 5 to 6. So this is 5 to 1, and you can see the TS diagram 5 to 1. The delta S reduces, the T reduces. So this brings the pressure and temperature down to the initial state, completing the cycle and preparing the cycle for the next compression. So what happens? Now you finished 1 to 2, 2 to 3, 3 to 4, 4 to 5. So that means to say the piston moved from the bottom dead center, moved to the top dead center, and again from the top dead center it came to bottom dead center. This is a cycle. So all these things, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 1 happens in this 2 cycles, whatever we do, 2 times the stroke length. referring to the PV diagram and TS diagram of a dual combustion cycle. Heat supplied is Q supply is MCV T3 plus T2 plus MCP T4 minus T3, heat supplied. So, it happens 2 to 3, 3 to 4, 2 to 3, 3 to 4, right. And then heat rejection happens only during the 5 to 1. So, it is 5 to 1. So, now efficiency is equal to 1 minus Q reject by Q in, which is nothing but 1 minus the entire cycle. So, that is nothing but 1 minus this, you just substitute everything and you get this equation. Now, I convert this MCP and MCV, they are removed and they are added as gamma. So, the efficiency is equal to 1 minus T1 T5 by T1. So, we convert this, divide by 1 outside. So, T1, so we try to get this term, and then T2 we try to divide, T3 we try to divide, we get this. Now, defining the volume ratio, RC, the compression ratio is nothing but V1 by V2, cutoff ratio rho is nothing but V4 by V5, V4 by V3, and the expansion ratio is V5 by V4, and the relationship is going to be this. So, the explosion ratio is rho alpha is equal to P3 by P2. So, recalling that what happens in 1 to 2, it is the same repeat: isentropic, isochronic, isobaric and isentropic. So, these are all reversible adiabatic compression, reversible adiabatic expansion, constant volume, constant pressure. So, we try to substitute all and then try to get this final equation as this form. So, it is observed that when rho equal to 1, we will get the expression for efficiency of Otto cycle. When rho is equal to 1. When alpha is equal to 1, we try to get the response of diesel cycle. So, this is why it is called as dual combustion cycle. So, the mean effective pressure, this is also very important. So, two things are very important: efficiency and PM, both are very important. So, PM is the mean effective pressure. So, mean effective pressure again is written in this form, right. Now, what we will do is, we will try to compare Otto cycle, diesel cycle and dual cycle. So, the Otto cycle, diesel cycle, dual cycle may be compared on the same compression ratio, same maximum cycle temperature, keeping the heat rejection as constant. So, same compression ratio with the same inlet condition and the same heat rejection. So, you can see here. So, it is PV diagram. So, it is 1 to 2, 2 to 3, 3 to 4, 4 to 5 and 5 to 1. The other one is 1 to 2, 2 to 6, 6 to 5, 5 to 1. The last one is 1 to 2, 2 to 7, 7 to 5, 5 to 1. So, this is the for the same compression ratio with the same inlet condition and the same heat rejection, we get the PV diagram. And this is the TS diagram, which is corresponding to the same thing: 1 to 2, 2 to 3, 3 to 4, 4 to 7, 7 to 1, 1 to 2, 2 to 7, 7 to 5, 5 to 1. So, the figure shows that Otto, diesel and dual combustion cycle being plotted on a PV and a TS diagram plane. It is observed that the area 1 to 2, 651, which represents the net work done by the Otto cycle. I told you 1 to 2, 2 to 6, 6 to 5, 5 to 1 is Otto cycle. So, let me write it: PV diagram 1, 2, 6, 5, 1 is Otto, right. Then it is the maximum, while the area 1, 2, 7, 5, 1 is for diesel. 1, 2, 7, 5, 1, 1, 2, 7, 5 and 1 is for diesel cycle, right. So, Similar observation is made in the TS plane of Otto cycle and diesel cycle. Thus, it is concluded that the same compression ratio and fixed inlet conditions and heat rejection, Otto cycle has the maximum efficiency. That is why we always go for petrol engine. So, you can see here Otto cycle's efficiency is greater than dual cycle than the diesel cycle, right. So, the same maximum cycle pressure and temperature with the same inlet condition and heat rejection, same compression ratio. Here it is same maximum cycle pressure and temperature with the same inlet condition and the same heat rejection. So, you can see here 1, 6, 4, 5, 1. The other one can be 1, 6, 2, 3, 4, 5, 1. The last one can be 1, 2, 7, 4, 5 and 1, 3 cycles. So, here 1, let us try to write the observation as 1, 1, 7, 4, 5, 1. The other one is 1, 6, 4, 5, 1. Okay, two cycles we are taking. Figure shows that PV and TS diagram plane for Otto, diesel and dual combustion cycle are plotted for the same maximum cycle pressure and temperature. So, it is observed 1, 7, 4, 5, 1 is the maximum, while 1, 6, 4, 5, 1 is minimum. So, what are we talking about? The area 1, 7, 4, 5, 1, 1, 6 is the minimum. So, this means that the net work done and the net heat transfer in diesel engine is maximum, while those of Otto cycle is minimum. So, this means that the net work done and the net heat transfer in diesel cycle is maximum. That is why we all the trucks are using diesel. Of course, there are other reasons, but this can be one of the reasons. This means that the net work done and the net heat transferred in diesel cycle is maximum as compared to that of a Otto cycle. Thus, it is concluded that for the same maximum cycle pressure and temperature, keeping the inlet constant and heat rejection constant, the diesel cycle has maximum efficiency. So, it says diesel cycle is having greater than dual than Otto cycle. If you see here, if you want to play safe, you can always have the dual cycle which comes in between. So, if you see here in the previous one, Otto was good, diesel was poor. So, if you see here, diesel is good and Otto is poor. So, this tries to give you a comparison feeling between the 3 cycles. Now, let us go to Brayton cycle. Brayton cycle is a theoretical cycle for a simple gas turbine system. Gas turbine, I told you in the power stations also they use gas. This cycle consists of 2 isentropic and 2 constant pressure process. The figure shows Brayton cycle on PV and TS coordinates. The cycle is similar to diesel cycle. Brayton cycle is similar to diesel cycle in compression and heat addition. It is very similar. The isentropic expansion of the diesel cycle is further extended, followed by a constant pressure heat rejection. The thermal efficiency is given by this formula. So, where is the difference? This is the 2 difference. So, the cycle is similar to diesel cycle in compression and heat addition. The isentropic expansion of the diesel cycle is further extended, followed by a constant pressure heat rejection. So, this is Brayton cycle. So, you will see here from 1 to 2 it goes isentropic process, 2 to 3 is adiabatic, 3 to 4 is isentropic process and 4 to 1 is the expansion process, right. So, you will see here there are 4 dash and 4. So, if you go by the TS diagram, you can see here 2 to 3 is a constant pressure process, 3 to 4 is a expansion process. So, wherein which I tap it at 4 dash, which is intermediate. From there I try to reduce it by constant volume going to 1, or the next one is I try to go down with a constant pressure. So, I maintain constant volume, it is 4 dash to 1. If I go with constant pressure, I come to the 4 and then I go to 1. So, this is Brayton cycle. So, isentropic compression is 1 to 2. In the first step, the air is compressed adiabatically in the compressor. This means that the compression happens without heat exchange. As the air is compressed, its pressure and temperature increases significantly. While the volume decreases, this prepares the air for effective combustion in the next stage. When we talk about constant pressure and heat addition 2 to 3, the high pressure air now enters combustion chamber, where fuel is added and burned at constant pressure. The combustion process causes a sharp rise in the temperature and volume. The heat added increases the internal energy of the gas, which makes it ready to do work during expansion. So, this please understand, high pressure air now enters the combustion chamber. When the fuel is added and burnt at a constant pressure, because we are adding heat, constant pressure, the combustion process causes a sharp rise in the temperature and volume. Sharp rise in the temperature and volume. Okay. So, then it is isentropic expansion. The high temperature, high pressure gas expands adiabatically in a turbine, performing work on a turbine blade. As the gas expands, the pressure and temperature falls down, and there is a energy transfer to the useful work. This is called as the power producing phase of a cycle. So, 3 to 4 is isentropic. The constant pressure rejection is after the expansion, the gas are released to the surrounding open cylinder. If it is closed cylinder, it is cooled and it is retaken into the system. So, in a heat exchanger, cooled in a heat exchanger in a closed loop system at a constant pressure, the temperature decreases, completing the cycle and preparing the air for the next compression cycle. Okay. So, this is Brayton cycle. So, Brayton cycle is this, where in which it talks about isoentropic compression, constant pressure heat addition, isentropic expansion and constant pressure heat rejection. So, now let us see how are these things deviated from the actual cycle. Compression, expansion are not frictionless adiabatic process. A certain amount of friction is always present. There is considerable heat transfer between the gas and the cylinder wall. So, there is a residual temperature. This residual temperature, we do not know what amount of residual temperature is there. Now, you restart the new cycle. So, the old residual, while the piston is moving to a certain height itself, can rise the temperature very high. So, the combustion can happen prior what was expected. So, that is what is a big deviation. The combustion does not occur either at constant volume or at a constant pressure. It never happens. This brings the next deviation. The thermodynamic property of the gas after combustion are different than those of the fuel-air mixture before combustion. So, the air density reduces, the air property reduces, the air becomes light. So, the thermodynamic property, so for example, while you are compressing, the air would have come at a certain speed. After the combustion is over, it exhausts at a much faster rate, possible. So, then there is a thermodynamic property of the working fluid changed. The combustion may be incomplete. Not all the diesel particles or the air particles gets burnt. So, now once it does not get burnt, so it again tries to bring you a residue and other things. The specific heat of the working fluid is never constant. It increases with temperature. How much does it increase? What is the exponential increase? Very hard to find out. So, now people are trying to use glass engines and try to see the combustion, how is it happening, how is it propagating through laser. So, they are trying to very precisely monitor, but still it cannot be found out by one laser. So, they have lasers as multiple planes. So, in one plane they try to take the temperature distribution and see how does a wave propagate. So, that is a challenge. Even now there is lot of work going on, and big auto industries work on more and more how to improve the efficiency of combustion. The cylinder pressure during exhaust process is higher than the atmosphere. As a result, more work has to be done by the piston on the gas to expel them out of the cylinder. Cylinder pressure during exhaust process is very high than the atmosphere. So, there is atmospheric pressure which is constant. Now, assume you are forcing air to go through. So, this fellow will resist, right. As a result, more work has to be done so that the fuel can easily go inside. For example, a crowd of people are there, they are standing. Now, you are pushing one person inside. So, when you are trying to push, you have to push him with more energy such that he gets into the crowd. More work has to be done by the piston on the gas to expel them out. So, there is a deviation. So, friends, in the two lectures, what did we see was, we saw what is a gas power cycle, what are the different types, what is a air standard power cycle, and what are its characteristics. Then, what is a Carnot cycle, its features, Stirling cycle, its features. Then, we understood what is Otto cycle, diesel cycle. Then, what is a dual combustion cycle, what is the comparison of Otto, diesel and dual cycle. Finally, we saw what is a Brayton cycle. Before we conclude, we also saw that whatever happens in reality, there is a major deviation from the theory. So, that is what we saw in the last slide. So, friends, now I have small observation things which I want you to do, because you have studied all these cycles. So, look at a truck which travels at 50 kilometer per hour with a tonnage of 100 tons load. It is going at 50 kilometers per hour. Now, you try to see what will be the torque it will generate for its motion with this load. This is just a simple calculation. You can try to see what will be the torque, what will be the energy which is required to be done such that it takes 100 ton on its back and run at 50 kilometers per hour. Just a simple calculation so that you know what is the energy and other things we are talking about. Try to look at a race car which is traveling at 200 kilometers per hour, and what is its torque. You can do some simple calculations with assumptions, or you can directly look at some specifications and then find out. Why does the race car have frequent filling of petrol or fuel, whatever it is, right? The third thing is, when we try to talk about diesel engine used in locomotive, what should be its mileage? Why is it so? For example, if the mileage is high, why is it high? If it is low, why is it low? And then if it is the same like normal car, why is it so? So, these three things, if you start looking into, then you will try to understand what makes this entire thermodynamics very important for an engineer. These are the references which we have used in preparing this chapter. Thank you very much.